My name is Kailash Raman, and today I'm going to tell you about the second of two companion papers on the semi-analytic inference of dwarf galaxy densities in the cold dark matter model. This is part 2, which focuses on the implications of our work for dark matter indirect detection constraints. This work was done with my collaborators, Benjamin Safdi, Dylan Folsom, Mariangela Lisanti, and Manoj Kaplinghat. As a reminder, Milky Way satellites are the smallest dark matter-dominated systems that we currently observe in the universe, and are therefore powerful probes of CDM and other dark matter models. This was a topic that was discussed in part 1. Satellites are also often used in searches for dark matter annihilation, which is the topic of this work. In particular, dwarf galaxies are used as a complementary probe for the parameter space relevant for the so-called Fermi-galactic center excess. The signal strength of annihilation is encapsulated by the astrophysical J factor, defined as the line of sight integral of the dark matter density squared. Our main result is that using SatGen, a semi-analytic satellite galaxy generator, to set a cosmologically informed prior for satellite density profiles yields dark matter annihilation constraints that weaken by a factor of 2 to 4 in the BB bar annihilation channel. As discussed in part 1, we generate a large sample of realistic Milky Way satellites with SatGen, assigning initial halo profiles and characteristics calibrated to cosmological simulations, and following the orbital evolution and tidal stripping of each satellite as it falls into the host. In part 1, we discussed assigning density profiles to real dwarf galaxies by conditioning the simulated halo population on observed satellite characteristics, such as the stellar mass and the mass contained within the half-light radius of the dwarf galaxy. In this work, we treat explicitly the idea that SatGen sets a cosmological prior for halo density profile parameters, and use this prior in genes analyses of dwarf galaxy kinematic data. For concreteness, we use as our prior the distribution of halos after conditioning on the stellar mass of a given dwarf galaxy. This differs from the common procedure of using wide log uniform priors on halo parameters that allow genes analyses to place satellites in unphysical dark matter halos. With this procedure, we can infer both astrophysical J factors and the angular extent of satellite J factor profiles. For the highest luminosity dwarf galaxies, the data are sufficiently constraining that the prior has minimal effects. For some of the largest J-factor ultrafaints, however, using the SatGen-informed prior can decrease the inferred J-factor by up to an order of magnitude. We also find that many satellites have angular extensions of around 1 degree, indicating that treating them as point sources in Fermi analyses is unjustified. As discussed earlier, using the J-factors computed with the SatGen-informed prior to recast existing analyses of Fermi data yields a factor of 2 to 4 weakening in the annihilation constraints. In particular, these results indicate that dwarf galaxies may not yet exclude the dark matter interpretation of the galactic center excess. Turning towards the future, we compare the observed distribution of J factors to the SatGen expectation and find that, taking the observed kinematics at face value, we have likely already seen all of the largest J factor dwarf galaxies. In summary, we find 3 main conclusions in our work. First, a cosmologically informed prior weakens annihilation constraints by a factor of 2 to 4. Second, a point source approximation for dwarf galaxies in Fermi-LAT data analyses is unjustified. Third, we have likely already seen the largest J-factor satellites. Thanks for your time, and if you haven't already, I encourage you to see part 1 on testing CDM.